Thanks a lot to the organizers for giving me this invitation. The subject is contact line modeling of drops moving on textured surfaces. It's a very interesting lecture earlier on liquid marbles. So this talk is similar but has a different application, and that relates to production of potable water, probably by thermal desalination or condensing moisture from air. So in an application, moist air flows over a cooler substrate, water condenses, and then we collect it. So the goal is to increase water productivity as much as possible. So preferably the surface is made hydrophobic, so that drops will form and drain away. So this process of dropwise condensation we studied a few years ago. So you get drops of various sizes. So there is nucleation, there is growth, there is coalescence, there is jumping, and then has to be raised. Okay, can you, I hope you can hear me. So the process of condensation generates a whole range of drop sizes. The large drops finally drain away, and that is the useful output of this technique. So we built an atmospheric water generator, tried out various surfaces. It turns out that the productivity goes up if the surface is super hydrophobic, as hydrophobic as possible, and at the same time the hysteresis should be as small as possible. When these conditions are fulfilled, productivity is very high. So under these conditions, you will have liquid drops formed on the condensing surface. So traditionally, this super hydrophobic texturing is generated by various types of coatings, but coatings tend to be short-lived. So even the one that we made on a copper substrate, you can see the SEM image here, but after a few cycles of drainage, it wears out. And super hydrophobic tends to become hydrophobic. Water productivity significantly falls. So we have been looking for alternatives to the use of coatings. We have ventured into making pillars. These are physically textured. If you're going to make it in a machine, it's preferable to have some kind of order, some pitch and height and cross-section. At least with the resources we have, we are able to make short pillars on silicon wafers, but when we move on to metallic surfaces, which is what is used in water production, the pillars are much larger. You can see its height could be 200 to 600 microns, while on silicon you may get 20 to 50 microns. Of course, with pillars in the millimeter range, the drops will go from, the surface will go from hydrophobic to hydrophilic and beyond. So we are presently working on, so this is a silicon wafer. You can see height is 50 microns. You can see the various types of images, most important being the drop whose equilibrium contact angle is 150 to 160 degrees. Hysteresis is as small as 10 degrees and lower. But we can't use it for dropwise condensation because it is, the conductivity is very low and the heat fluxes through the silicon material will be small. Thermal resistance is high. So we have tried out metallic substrates, but as I mentioned, the dimensions are higher, but they still produce a fair level of hydrophobicity. But this is under equilibrium conditions. If you gently place a drop, it sits on top of the pillars. But dropwise condensation has, it's an active process like the cycle I showed. Drops are growing and then they may slide, they may bounce off, they may recoil. So it's now known that drops, depending on how the pillars, the dimensions are arranged, the drop may sit on the pillars or the liquid may end up filling the interpillar gap. It's called Cassie-Baxter and Wenzel states. From the condensation perspective, I said superhydrophobicity is to be preferred because then the largest drops formed during condensation are very small. The thermal resistance of the drop is small, cycle time is small, overall productivity goes up, water productivity. So, but will that conclusion hold for pillared surfaces? That's what we are looking for. For chemically textured surfaces or coatings, that is certainly true. So if you do a little bit of analysis, it turns out that there is a critical height which depends on the equilibrium contact angle of the bare substrate. Critical height below which the drop sits in the Wenzel state, above which it sits in the Cassie-Baxter state. And Cassie-Baxter gives a higher contact angle. That means this is the, so it's more hydrophobic than Wenzel. But the difficulty is that pillars contribute to hysteresis. They contribute to pinning, mainly at the corners. So as the number of pillars or the size of the pillars increases, there is pinning, and therefore the drops get retained over the surface. So it's not necessary that superhydrophobicity will give rise to a higher level of water production. So this picture here shows why pinning will happen at the corner. So this contact line is moving on the substrate. and then it has to start moving on the side vertically downward, and at the corner the residence time is finite. So let me show a short video. This is for a glaco coated surface which is super hydrophobic, low hysteresis. So here you will see that the drop spreads a little bit. It's forever moving. So, and there is also a recoil during the spreading process. So it's the 7,500 frames per second video. Focus on the footprint, that is the base, which changes with time in a somewhat oscillatory manner. And there is also some bouncing off. So let me contrast this video with drops spreading on a sticky PDMS surface. So here you will see that the drop spreads a little bit and gets pinned. So the footprint then becomes constant. So this is drop spreading, and then the footprint it becomes immobile on the substrate. So when you go for a pillared surface, here you will see that both effects are present. So it's a little more complicated than just super hydrophobic or a sticky substrate. Both happen, and then as you change the pillar geometry, pinning is augmented, and you see a whole lot of newer patterns. But the big question is, will it increase water production? That's we don't have an answer yet. That's the question we have set for ourselves. So you can see the video. I think I prefer to show this because those pillars are visible in this here. So this spreading in a way is interrupted because the contact line has to jump from one pillar to another. So pillars also have greater variety of new phenomena. For example, in condensation, if you have some liquid retained in the interpillar gap and then there is a drop growing on it, the pressure difference outside is less, inside is higher, and the drop is ejected. So your drop jumping, that is the phenomenon seen. So this video will show you. Pay attention to that arrow, yellow arrow, and you will see the ejection of the drop. Similar things happen when you have coalescence. Coalescence is a big deal in drop-wise condensation because you have thousands of drops on the surface adjacent to each other. So there also you see the bouncing off. So it's not possible to do thousands of experiments, so we started looking at having a simulation framework. So we are in the Navier-Stokes regime. Interface, the surface tension at the liquid gas interface is treated as a body force term. The big unknown is the treatment of how the contact line moves. So there was reference to one paper by Scriven. I think the term used is contact line singularity because the no-slip condition is violated at that point. So it requires special treatment, and what should that treatment be? So that's called contact angle modeling. So we have spent time thinking about how the contact line can be modeled, because this drop surface interaction plays an important role for condensation. So when you carry out the simulations, it's just a sample. This first row is experiments, second row is simulations. You can see that it's a fair match between the two, but the drop shapes, the drop gets significantly deformed. By the way, the liquid we have considered is water in all the studies that I'm going to discuss here. So a whole lot of experimental data is available on how contact angle model can be set up. Essentially, the model is prescribed as a function of capillary number. This right hand side, this is experimental data. You can see a lot of variation, depends on the choice of the substrate, depends on the choice of the liquid, depends on the choice of the surrounding medium. For us, it is air, the ambient. Experiments were carried out in air. Water is the, or DI water as the liquid. So this is a picture of hysteresis. This hysteresis is generally defined as advancing minus receding angles when the drop is on an incline. So there are alternatives to it. That's one typical definition. So this data is 2015, but prior to it, people had set up some models, essentially to model this little. You can see that on the positive side, contact angle increases with capillary number. So that part was modeled. But even these authors of 2015, they concluded that this Cox-Voinov model and the MKT model, these in a way represented experimental data fairly well, but not very well. So recently we have proposed a very elaborate contact angle model, which includes slip length, which is characteristic of the surface. It includes friction, contact line friction, and also includes hysteresis, which is that C-pin, pinning coefficient. So first I'll show you a little bit of our success story in using this model to represent drop spreading. So this is comparison with the experiments of others. You can see this, all the circles are, the symbols are experiments, and the solid line is our simulation. The right hand side, left is a hydrophobic surface or a wetting surface. Right hand side is a sticky surface, PDMS type surface. This blue line is the Kistler model, the original Kistler model. There are variations also to it, but the original Kistler model does not show the oscillations arising from pinning, but those open circles are our model. We have set up experiments. We have tried out, just to test the contact angle model, we tried out surfaces with coatings, glaco, fluoropel, and then we also did PDMS and bare glass. But I'll essentially compare glaco and PDMS. There are two extremes. Glaco being super hydrophobic with low hysteresis, and PDMS being hydrophobic but sticky with high hysteresis. So in general, what happens during spreading is drop spreading. So you keep the drop on the surface and collect the video sequence. There is some spreading. If the surface has spinning, then the footprint freezes in time, and there are so-called capillary waves on the interface. So essentially, during pinning, there is a jump in the contact angle going from, let's say, capillary number going from positive to negative. At capillary number equal to 0, it's a jump in the contact angle. But our model, in a way, smooths the whole thing. If you put a jump in the numerical simulation, there could be some consequences. So this green line and green symbols, that is on the glaco surface. So the line is our simulation, and the symbols are from our own experiments. While PDMS is this star, this is the PDMS jump because of hysteresis, and that is the positive branch of the contact angle model. So, but I showed you the entire video, so you can analyze the video frame by frame. You can measure the footprint, you can measure the contact angles using image processing tools. So this is and it's by the way, it's an axisymmetric simulation. That here it's axisymmetric, drop is spreading equally on all sides. So these symbols are experiments, and the solid line is simulation. First one is glaco, and here is PDMS, where you can see much larger oscillations, and the solid line, which is based on our proposed contact angle model, also does well. So just to show that spreading ratio, so for PDMS you can see that it has become a constant because of in a way it's frozen, it is pinned at the contact line. And I have shown you data only up to 100 milliseconds. If you wait long enough, it will approach equilibrium. So that may happen over, let's say, 2 seconds of time. So I'm just showing you the initial part of spreading. So of course, if you want to test simulations versus experiments, you have to match the interface shapes. The first one is glaco, super hydrophobic, low hysteresis, with a little bit of a recoil. In experiments, it happens. First row is experiments, second row is simulations. There is recoil happening at practically the same time instant. So if you have to match the instant of recoil. You also have to match the height of recoil, duration of recoil. And third is this part C is PDMS, where the base gets frozen and there are height oscillations of the drop. So, this Weber number is an important quantity where the drop may get ejected and fall back. So, then you want to know how spreading is impacted. So, this is with an experiment of from the literature. I think this picture I showed you earlier, we were able to get a good match. You can see here also the spreading pattern, symbols versus continuous line. It's quite good. Of course, this result is limited by the Weber number. You can't go to very high Weber numbers because then you will have splashing, particularly in water. So, we are not in that regime. Here the drop integrity is maintained. So, our present work extends both experiments and simulations of drop spreading as well as coalescence as well as impact on pillared surfaces. So, naturally, it's a 3D simulation now, though our imaging is also one view imaging. This simulation time sharply increases. So, we first compared with recent experiments, 2012, with some impact, 1.17, 1.89. Pillar spacing is about, these are all small pillars. Experiments were carried out on that silicon wafer. There is no heat transfer, no condensation. So, you can see here that pillar spacing has gone up. So, one of the results that even the equilibrium analysis shows is as pillars become tall relative to the pitch. That means deep pillars will encourage Cassie-Baxter, because then the liquid cannot fully infuse into the interpillar gap. So, this second row is more wettable than the first. So, we were able to get a good match between experiments and our simulations for the pillar geometry. So, equilibrium analysis shows that there is a critical pillar height, below which it is Wenzel, beyond which it is Cassie-Baxter. But when you do this drop spreading, it turns out that the transition is not that sharp. There is a fairly broad, partially wetting regime. And depending on how the drop approaches the surface, it may head towards the Cassie-Baxter state or may go towards the Wenzel state. But the result that tall pillars will encourage higher levels of hydrophobicity compared to short relative to the pitch. That result comes out through, we may call them dynamic simulations, not equilibrium, not static simulations. And hysteresis, now for pillars, I mentioned hysteresis is higher because of the pillar corners. So, this is the wetting diameter. So, finally, in Cassie you attain some equilibrium state, Wenzel also you attain some equilibrium state, but there could be a multitude of partially wetting conditions, and each could have its own unique solution depending on initial conditions. Initial conditions would be how the drop approaches the surface. So you have to distinguish between the hysteresis because of corners with the hysteresis of the bare surface itself. But in general, a higher level of hysteresis will induce rather the other way, lower level of hysteresis will induce oscillations. Higher level will lead to pinning. Okay, so the information we gathered from the drop surface interaction studies were brought into drop-wise condensation modeling. So you can see this is the Wenzel state and this is the Cassie state. Overall, I think I did mention that higher levels of hydrophobicity will make the critical drop size smaller. So here, even though schematically they are shown to be the same, here drops are smaller compared to Wenzel. Here you have liquid filling the interpillar gap. Here it is either vapor or air. If it's moist air condensation, it is mainly air. So because of air, thermal resistance in Cassie is actually higher. So it's not automatic that water productivity with Cassie would be greater. So in the analysis, all these factors are brought in, along with coalescence time scales, possibility of jumping, and so on, to come up with a it's kind of an integrated condensation model. So Milkovich probably studied dropwise condensation with small pillars, 6 microns height, on silicon wafers, and showed that the superhydrophobic, this is Cassie Baxter, actually will give you lower wall heat fluxes compared to a normal surface. So that was a kind of a negative outcome. For pillared surfaces. Okay. These are short pillars. And of course, in that study, it was shown that partially wetting surfaces will have water in the interpillar gap, and therefore conductivity, the thermal resistance may go down. But those are all for small pillars with silicon. Now, we wanted to see the same thing for metallic surfaces where pillars necessarily are, that's the state of manufacturing, pillars are larger. So we carried out that analysis. Just a summary. This is for a plane surface, and they are all to scale. You can see that in Cassie Baxter, the drops are smaller, so thermal resistance is smaller. So we expect higher productivity, but because of air resistance, the heat fluxes actually can be expected to go down. While for Wenzel, it's somewhere in between. You can also see that the time scale for Cassie is the smallest, 11 compared to 25 for plane, and goes up where water gets trapped in the interpillar gap. So we carried out a lot of analysis of this data. This is simulation data And we have, at this moment, we have experimental data for the plane surface, and we have validated the dropwise condensation model for a plane surface. That I am not showing here because I have not given you the details of that model. But this is water productivity as a function of degree of subcooling. By the way, there is a huge difference between condensation of pure vapor and moist air. So we have validated our model for both, but this data is for vapor.
Professor Muralidhar, you have 2 more minutes.
Thank you. So here we have compared smooth, Cassie and Wenzel for the dimensions we have chosen, and because our substrate is copper, thermal resistance does not go down, does not increase excessively. It's sort of comparable, that's where we are. But actually what we want is Cassie Baxter to outperform the smooth surface. So we have to try out other surfaces, and we have to make the pillar height smaller so the conduction resistance goes down. But that will require us to make the pitch very, very small. That is the hardest step in manufacturing. So this is where we are. So if you invite me for the next ICOM, then I will show you the dropwise condensation data on pillared surfaces, and I will work for it. So yeah, so we spent a lot of time on contact angle modeling, a lot of time on drop interaction with textured surfaces, put all that information into dropwise condensation modeling, and we try to see if water productivity would go up. So independently, we are also working on solar-based water purification processes where you have both evaporation and condensation. So yeah, future work, this fabrication is what is, at least my own background is not fabrication, but trying to get into it to see if the pitch can be made in metals, if it can be made. We have tried wire cut EDM, we are trying laser etching and so on. So, but this has to be scalable because the condensing surface will be large. So yeah, finally that question has to be answered on whether pillared and patterned surfaces will help improve performance of water purification devices in general and this atmospheric water generator in particular. Yeah, thank you very much.
Thank you, Professor Muralidhar, for the interesting talk. So now the floor is open to questions.
Thank you for the interesting talk. How do you model the contact angle for the pillared surface? Because there you will have to impose the contact angle boundary on the vertical wall of the pillars also.
Right, yeah. So you have to keep track of the contact line as it goes over the surface, gets pinned, and then starts moving down the wall, and then after some time reaches the lower wall. So usually our students submit the simulation file and go home. Takes a huge amount of time. So yeah, I mean that is, you may call it a brute force approach. We are tracking the contact line on the surface. Yeah, though we are looking for equivalent approaches, but that is another story. Can the pillared surface be replaced by an equivalent flat surface? Then your simulation reduces to a few hours from several weeks. It's mainly because it is 3D versus axisymmetric. Still thinking about it.
Yeah, that's the question that, presumably your simulations are 2D.
No. For pillar it is 3D.
Yeah, so for pillar it is full 3D.
Full 3D, yeah.
Okay. So then is it possible to do things like,
if the pillars are not straight?
Right. So it's a question of mesh generation. You have to generate.
Is it a dynamic mesh generation? I mean, as the, because what happens near the boundaries and near the contact lines is very important. So, but when the droplet moves, under the condition of moving, so you need to move the mesh. Mesh also should be moving mesh?
Okay, so there are two types of simulations. One is spreading simulation, and then there is simulation for a continuously moving drop. So for the continuously moving drop, there is a moving mesh treatment. But for the spreading, our time scale is also, let's say, 0 to 100 milliseconds. Over that small time scale, the movement is not excessive. So the mesh is fixed.
Thank you for the talk, sir. So you are simulating all this with very realistic fluids, like with a high density ratio, right? And
water and air.
Water and air. So almost 1,000. So this, how about the spurious current in the interface? Because surface tension forces in any modeling will always cause those.
Yeah, these are capillary waves which are surface tension, have surface tension as the origin. Yeah.
So,
and because of pinning, if you think of a string, if you just fix it, then a wave will travel back.
So
that is the tension in the spring and tension at the interface, they are similar.
So how do you distinguish between which are numerical artifacts of the spurious current and which is coming from the actual pinning?
There is only one way of doing it, which is mesh refinement. Okay, so of course, so then there is that phase field method which has its own parameters that will help you narrow down the interface width. So that a numerical, so it's not just one simulation, you have to do large number of simulations, so you gain experience. But the answers are, you have to refine the mesh, and then you have to, that high speed, that is high speed visualization. We have 7,500 frames per second. But if you read the latest papers, they go up to 20,000 frames per second. They will resolve every aspect of the capillary wave. But we see that at least the large amplitude, there could be some minor spurious oscillations numerically, but we are only comparing the overall, the large amplitude fluctuation. Yeah.
Thank you.
Hi. Thanks for a very interesting talk. So I have two questions. One was on your correction to the Cox-Voinov model that you showed. So if I understood it, apparently you provided a correction or expression for the local contact angle. So I was wondering what was the physical basis that went into that correction, because I could see there was one C and it was also dependent on the capillary number itself. And the second question is on your condensation part. So when drops condense, the size distribution is self-similar in time. The growth of the drops is, they form a very beautiful pattern which is self-similar in time, and you have a scaling. So I was wondering that on a pattern substrate, now that you introduce another length scale, so the size distribution that you will get, will it have the same self-similar scaling that's classically we know, or will it have something for different scaling?
Okay, so let's start with condensation. See, in this water condensation, water production application, the interest is really on the large drops. That is what gives you that's what will slide away and you get the output. And the smallest drops are in the nanometer. Largest ones could be a few millimeters, and the smallest is in the nanometer scale. So that universal scaling that you are referring to I'm not sure if it is strictly valid. It is valid in some range in between that you can use as an approximation. So our approach has been to do this kind of multi-scale simulation, go from the nanometer range all the way to the millimeter range. So that is, we have not used any scaling law.
No.
But
So
we can get the scaling law out of it.
so when the drops grow,
No,
they
but,
grow by coalescence.
right.
So I think you will get the scaling in that regime where
No,
the drops are.
drops initially will grow because of direct
No.
condensation.
After,
After that, then there is also the drainage.
in between.
No, when the drops drain, they also wash away all the little drops along the path. So there is like a major disruption to the condensation event or condensation process. Major disruption in terms of an event is by sweeping away of the small drops. So that scaling we have seen before instability, not before coalescence. Coalescence is happening everywhere. But these large drops, they keep sweeping the surface. But despite that, your question was, will there be a regular pattern? So since the largest drop is, let's say 1 or 2 millimeters, it is much larger than the pillar size. So we think that the overall process, so the scaling law may change, but the sequence of events is likely to be the same. Yeah. Yeah, and how did we derive the contact angle model? I will request you to look at the paper. But we relied on that MKT, molecular kinetic theory approach, which has all the kinetic theory parameters. Those we lumped into one single parameter that is surface specific. It's anyway surface specific. So we made it a surface specific parameter that has to be determined for each test surface you consider.
Thank you.
The root is in that kinetic theory, molecular paper, that other paper.
Thank you.
Okay. All right. So there have been some recent studies that have infused oil into the interpillar gaps. Do you think that your model can be applied for that situation, or like you need some fine tuning? Are you familiar with the oil infused?
Lubricant infused surfaces or self-lubricated surfaces. Yeah. Slippings, yeah, with slip. Yeah. See, whether it is drop level interactions or at the scale of condensation, there are some macroscopic continuum level quantities that you have to prescribe, like equilibrium contact angle, pinning coefficient or hysteresis, advancing, receding angles. And then there is a friction coefficient at the three-phase contact line. As long as the drop is larger than the pillar dimensions and larger than the interpillar gap where that lubricant is placed, then I think this continuum level treatment, I think, will hold. So the condition is you should be able to, well, the drop has to be large compared to the pitch of the pillars where that high viscosity liquid is infused. But in the water production context, the experts said, do not bring oil into the picture.
All right. Thank you.
Thank you everyone for the stimulating discussion. So in the interest of time, we are going to close the session, but we can always have a discussion after that. And so once again, a round of applause to Professor K. Muralidhar.
Thank you.
There is a small token of appreciation as well.